Sorry about the interruption. I had an important phone call, but that's okay. We have this nonlinear system, and we followed this path, y equals 0, and then x equals 0. And over here we had x equals 1. We can substitute into here. We got y squared equals 2, and so we got y equals plus or minus square root of 2. So altogether, we can make a record of our critical points. We have 0, 0. F of 0, 0, which is 0. And then we also have 1 radical 2, F of 1 radical 2, and also 1 negative radical 2, F of 1 negative radical 2. So we have 3 critical points. And the question is, what are they? Well, we can apply the second partials test. We'll do that right in the middle here. D is fxx. Let's see, the second x partial is 2. The second y partial is negative 2x plus 2. Minus, now the mixed partial, we could do a y partial of this, negative 2y squared. And now we can simplify this a little bit. I'll keep this in factored form. Minus 4y squared. The square gets rid of that negative 2. Now, as far as this one, d of 0, 0 is equal to 2 times 2 minus 0 equals 4, which is greater than 0. It's a max or a min. Now we can grab the second x partial, fxx, at 0, 0 is 2. You could actually, incidentally, you could also use the second y partial here. It doesn't matter. You're really checking the concavity. Positive means it's concave up, and if it's a min or a max, the concavity is going to be the same in the x or the y direction. So, which is greater than 0. So we're at a relative minimum. So I'm just going to write relative minimum right here. Space is at a premium here, so. On to our second point. D was equal to, I erased my D, I should have kept that. The second x partial is 2. The second y partial is negative 2x plus 2. And then we had minus 4y squared. It was the mixed partial, negative 2y quantity squared. Now, we want to plug this in. D of 1 radical 2 is 2 times, now if we plug 1 in, we get 0, minus 4 times radical 2 squared, and that's 2, that's negative 8, less than 0, and guess what, that is a saddle point. So we have this weird looking surface. This is really a third degree surface. We have the saddle point here, and d of 1 negative radical 2 equals 2 times 0 minus 4 times negative radical 2 squared. Okay, and guess what? That's another saddle point. It's got to be a pretty weird looking surface. We have a relative minimum of 2 saddle points according to our analysis. So go to Wolfram or find a 3D grafting utility, graph this surface, and you can understand, probably see how, it's very easy to find something like that online, and you'll see the minimum saddle point. So that's all. We'll be back for part 2. We'll talk about absolute maximums and minimums on a closed bounded region.